We will be recording this webinar to make it accessible to our community of practice members in the near future. Before we begin, it is a pleasure for me to introduce myself. My name is Ruchi Shah. I'm a scientific project manager at ILSI Europe. Today, we have with us our special guest speaker, Dr. Dieter Fischer, who works at the Leipzig Institute of Polymer Research, Dresden, and is an expert in polymer analytic chemistry, specializing in spectroscopic methods, especially in FTIR and Raman microscopy. He has extensive experience in multivariant data analysis, including quantitative analysis, statistical process control, and real-time process analysis. His research focuses on microplastic particle identification and quantification by automated analytical methods enhanced by machine learning algorithm. He is involved in the Microplex Food Cornet project, where SOPs, analytical methods for the investigation of complex food, will be developed. We also have Dr. Marchesi from Tetra Pak. He's unavailable to speak at the moment because he has got a little flu. I hope we can have him of the Q&A. The objective of a webinar, we are gathered here with a goal to learn and spread more knowledge on analytical methods for microplastics detection in food. We will also engage with experts from ILSI Europe Microplastics community of practice and moreover to network within the experts in the field. ILSI Europe's mission is to provide science-based guidance to the food sector by fostering collaboration between industry, academia, and government. Brings experts together with different point of view, different stakes of interests, different opinions, build consensus based on science and evidence available. ILSI Europe is one of the branches of a global entity based in the following locations around the globe. Our portfolio of activities constitutes pre-competitive topics on food safety, nutrition, sustainability, along with EU-funded projects. ILSI Europe follows strict scientific integrity principles that apply to all ILSI Europe's activities, including inclusivity and transparency. As a non-profit organization, ILSI Europe operates through in-kind contributions of experts and relies on financial support mainly from corporations and institutions. The design, review, and execution of ILSI Europe's scientific research proposals and activities are independent from the funding sources. We publish impactful science-based guidance available to access throughout our website. Our communication and dissemination activities have deliverable throughout our network, and our dissemination activities have various forms. Today's webinar is sponsored by ILSI Europe Microplastics Community of Practice, available on LinkedIn. Many say that what triggered the development of the community of practice. There are many initiatives in the past few years where funding has been finished and often the network falls apart. There is a need to exchange among these experts and use resources efficiently. Hence, we have launched the community of practice. The objectives of the community of practice is to connect and exchange scientific knowledge and the latest advances in the field of nano and microplastic particles, create synergies, drive the field to advance knowledge on micro and nanoplastics in food and beverages with the ultimate goal of safeguarding human health. The focus of the community of practice relies on four major areas of the subject: the analytics, the exposure of microplastics, biomonitoring, and health impact of the same. The community of practice has benefits of staying up to date to the science. We give awareness on upcoming events, initiatives, and calls. We obtain critical insights from experts on your question and thoughts. We find experts to collaborate with and gain visibility by sharing our research. To join the community of practice on the LinkedIn, please scan the QR code and you will be able to go through the page. The activities of community of practice include quarterly roundtable discussions, webinars such as today, a summary or a link to recent scientific papers, critical discussions around these papers, announcement of events, project calls and initiatives, and educational materials. All COP members are invited to be a part of these resources and share their own knowledge. The community of practice members have access to today's webinar. They will also be able to access the upcoming webinars. As I said, it is a series of webinars. The next webinar in April 2025 will be subjected to the critical overview of exposure of microplastics to human brain, followed by a webinar in June 2025, which will be based on biomonitoring of microplastics, which will be later followed by in-person workshop in September, which gives a one-on-one interactions, enables discussions on critical topics, grows your networks as well. We end the year with another webinar on health impact of microplastics in food. If you are an industry member and you want to go further, the community of practice is open and available until the 31st of August 2025. As an industry member, to continue having access to the Microplastics Initiative Task Force, the activities we invite you to join Microplastics Initiative itself. The Microplastic Initiatives right now has members from Tetra Pak, AB InBev, Dow, Food Context Center, Nanon, Imperial College London, and Wageningen University. They drive the topics and focus on the community of practice. They initiate, develop, and manage new activity proposals coming out of these community of practice discussions and actively participate to expert groups and develop the publications and the focus areas for them. Joining ILSI Europe as an industry member gives a platform for distinctive networking collaboration with experts from academia, public authorities, and civil society, along with your fellow industry members. Experts get a voice on the table with relevant stakeholders and be a part of science-based solutions. I hereon invite Dr. Dieter Fischer to share his screen and continue with the webinar.
Yeah, good morning, everyone.
Good morning.
So I hope you can see my screen.
Crystal clear.
Yeah, and I will speak about a little bit about over the analytical methods for detecting and quantifying microplastics in food. The main topics are the spectroscopic techniques, Pyrolsis-GC, and also about the evaluation by database search or machine learning applications. First, I come from the Leibniz Institute of Polymer Research, Dresden in Germany. And there is a group, a research group. I'm the head of this research group, Microplastics and Spectroscopy, in the division of macromolecular chemistry. Our grants and the research support comes from different sources, from European Union programs, from money from the industry, and so on. So the subtitle of my lecture is I would give you a comparison of mass-based and particle-based microplastic analysis methods. The advantages and the disadvantages. First question is always, if we use analysis of microplastics, which polymers, how much, how big, and which shape. And for all that, we need a reliable determination with analytical methods. In principle, we have two detection methods, the so-called mass-based methods. That means methods for the determination of the total content. This is mostly for the microplastics analysis, Pyrolsis-GC or thermal extraction desorption GCMS. And the result of this is always a mass per volume or a mass per total dry mass. We have no information about particle numbers and size distribution. The second methods are the particle-based methods. That means methods regarding particle number, particle size, and particle size distributions. This is mostly we use for that FTIR and Raman spectroscopy. However, you can also use fluorescence microscopy for that. And here are the results, microplastic numbers with the size distribution for sampled waters. That means number per liter or per dry matter number per gram or kilogram. If we go a little bit more in detail, if we go to the particle-based method, it's shown here for Raman, for example. The problem is always a detection limit. If we have, for example, a polyethylene particle with a diameter of 7.5 micrometer, the mass of this particle is only 0.2 nanograms. That means to reach the detection limit for mass-based method, you need 500 particles that you reach this limit of 0.1 micrograms. However, the disadvantage of the spectroscopic methods is to accomplish appropriate particle numbers, you need an intensive workup procedure like density separation, digestion, subsampling, and so on. I come to this later. If we go to the thermo-analytical methods like Pyrolsis-GC, you see the detection limit is around 100 nanograms. And if you have only small particles in a sample, then you can see here, to reach the limits for the quantification, sampling needs to be adjusted for a longer time or a workup is needed. What are the challenges for the analysis of microplastics? Very shortly, we have an influence of the sampling, which sample amount we have, the place and the time. We have a great influence of the sample pretreatment. That means which pretreatment methods we use for the removal of inorganic and organic matrix without destroying the microplastic particles. Then we have an influence of the environment during sampling, pretreatment, and analysis. That means we should have a loss-free sampling transport. We have to use everyday blank samples in all steps until the lab and also in the lab. And you should use, especially if you go to microplastics and nanoplastics below 10 microns, to a microplastic-free laboratory for filtration, measurement, and so on. And best way is to have a clean room. A clean room is necessary if you go below 2 microns. To the sample pretreatment, mostly if you have an inorganic matrix, you need a density separation. And for removing organic matrix, what is in food samples very often, you can use the Fenton's reaction with peroxide. You can use KOH, but mostly you have to use to remove fatty acids and so on, and enzymatic treatment by different cellulases, lipase, protease, and so on. This should show you why we use a density separation for the inorganic matrix. Often you see a filter before and after the density separation, and you can imagine an analysis without is not possible. Then second point, what are challenges in the analysis is how accurate are the spectroscopic particle-based analytical methods. Here we have an influence of the filter material. You can use anodisc, silicon filter, gold filters, and so on. And very important is also the filter design. The pore size and the distance between the pores is shown here. And what you should do a fractional vacuum filtration to divide the microplastic particles in size fractions, maybe below 5 microns, between 5 and 10, 10 and 20. Otherwise, bigger particles overlay smaller ones. And very important is the role of the time factor during an analysis. If we have maybe a milk or so, and we filter this, then we have up to 100,000 particles per sample, and less than 1% is microplastic. So an automation of the measurement is crucial. But I will come to this also later. You need analysis with a statistical relevant number of particles. And last point for the challenges are how comparable are the results from different FTIR and Raman devices. If you use Raman, different laser wavelengths. Very important point is the subsampling, how much of a surface or how much from the particles on a filter must be measured for analysis. And last is which evaluation process you use, a classical spectral database search or a machine learning approach. In principle, if you use spectroscopic methods for particles below 500 microns, you can use a chemical imaging or a particle-based measurement. Imaging is mostly used in FTIR because you can use a focal plane array detector, and the particle measurement is mostly used for Raman. For FTIR, as shown here very quickly, you have a focal plane array detector and you can simultaneously measure 4,000 spectra at the same time. This is a great advantage in time, but the disadvantage for FTIR is that you can only measure particles bigger than 10 microns. This is shown here on a very short example. You have here a tissue from a muscle and some particles inside, and then you do on the right side the FTIR imaging, and you can see that in red are the spectra of polyethylene, and you can prove that by the spectra and found it. If we go to the particle measurement, the way is another way. This is a so-called combination of optical particle analysis and Raman or FTIR spectroscopy. Both is possible. We use for that two different programs. One is the GPOT, it's an open source software. Everybody can use it. Around 20 laboratories in Europe use already the software which is developed at our institute. And the second one is the Particle Scout. It's a commercial software from Oxford Instruments, WITEC. Both programs work so that at first we have an optical particle identification, and we can determine all particles in shape and dimension. That means X, Y, and Z coordinates, and store these coordinates for the subsequent Raman measurement. And for this optical particle identification, we use advanced algorithm like watershed or neural networks that you can distinguish between particles which are very near. Both programs identify then the particles on the filter after the Raman measurement using spectral databases. Here we use databases which include polymers, fillers, inorganic, organic substance, pigments, all the substances which also can be in food. Or we use a so-called random forest machine learning program. Here is shown that the spectral search very easily do a spectral search, and the program to automatically identify the particle. In this case, is a particle with a PVC. And then you can combine all the optical informations, the size of the particle, the shape, with the chemical informations. We can also identify fibers and you can bring this then to a database. At the end, you have for every sample the numbers of particles, for example, here 77 polypropylene in the sample, and also the particle size distribution for every polymer. And if you want, you can go to every information to every particle. If you use a machine learning approach, it's very easy. You can also use the spectral data and put in this data directly in the machine learning tool, and within seconds you have the result. This is available for auditing and commenting. The advantage is here that you can use the raw spectra from the measurement as shown here, for example, that you can see that is polyethylene. A very important point is subsampling. A lot of people use, because we have so much particles and the measurement time can be between 2 hours and 5 days. We tested different algorithms, and the main results are 50% of the particles or of the filter area, both is possible, should be analyzed for an error below 20%. Surprisingly, we tested 7 different approaches. 2 are shown here, for example, and all have similar results. That means the average subsampling error easily exceeds 50% if you measure only 5% or less of the particles on your filter, what is very often to see in papers about microplastic analysis. You have to be that in mind. An increasing of the microplastic fraction of the sample increases automatically the analytical accuracy. A very important point is also if you have food samples from a factory, for example, or so on, when you have hundreds of samples and every sample has thousands of particles, you need a database that you can use the samples for analysis and so on after that. This is shown here on an example for a marine plastics database. All the particle data from every sample were uploaded to a server where the database is, and querying results can be directly from the server for reproducible and data analysis workflows. And then you can use this data, for example, for geospatial modeling, for example, for environmental predictions of microplastic distributions. What is also very important, if different laboratories work together or on the same topic or the same project, how comparable are the results of these laboratories? For that, we need interlaboratory tests, and we can be sure that we have similar results. And for this interlaboratory tests, we developed a new approach. It's a concept of immobilization of particles on silicon wafer, for example, with the help of an inorganic adhesive. And you can use silicon filters or anodisk filters. A laser engraving define precise the measurement area, and all the samples are resilient, which they can withstand rinsing with water and cleaning, and you can send the sample from laboratory to laboratory. That every laboratory has the same, and at the end, the first can prove if all the particles on the filter. We did a first ring trial for that, and we could lower the observed variations between the participant results 70% lower compared to a parallel ring trail where everybody gets a sample and analyze the sample by yourself. So that is a very good idea for particle-based laboratory tests. Here's first results between 3 laboratories with FTIR, with Raman, with spectral database search, with machine learning. And you can see that the results are comparable. what you see on the first view, the light blue has too low values. And what we learned from this was, this laboratory was the only laboratory which used anodisk. All other used silicon filters. So if you use a machine learning approach, you have also to learn the filter material to the evaluation. Second method, which we can use, is the mass-based method. In this case, for food samples, only Pyrolsis-GC is a method. In principle, pyrolysis is a very complex process. You have intercompound and surface interactions that comes to signal interferences. In principle, you can measure a food sample, for example, directly in the sample cup, but then you have so much interferences so that also a pretreatment is necessary. How works a Pyrolsis-GC is shown here. We have a thermal decomposition of the polymers, and then we have generation of characteristic indicator products. This is not so easy to find the right indicators. On the right side, you see at the beginning, you have a total ion chromatogram. Then you can identify, extract from this indicator ions for special polymers. From this, you do a mass spectrum with indicator products. Then you have identified the polymer, but what we want is also a quantification, and for this quantification, you need a calibration with internal standards and so on, and this is can also be very time-consuming. At the end, you have mass-based concentration of polymer clusters. Because we have not for every polymer here an indicator, we have to generate so-called polymer clusters. That means that some polymers have similar indicators, and you have to put it in a cluster. The next problem for the quantification is you have a lower and a higher detection limit. You have always a range, and this range is for every cluster different. It can be for PET 30 nanograms per gram. And for example, for polyethylene, only 1,000 nanograms, or 1 microgram per gram. So it's different, and the indicators for polyethylene and for PVC are always in discussion. If you have, here are the clusters. That means you have an environment, also in a food sample, ambient air, also polymers, paints, adhesives, and so on, sealing materials. And then you see here which polymers are in the same cluster, and the clusters are also shown on the red side, because only for this 10 clusters we have indicators. The advantage of this method is you can also identify tire wear particles. So what we do is mass dissemination. Then at the end, we have a mass-related data given as mass of a polymer cluster in a given sample. However, you have also critical questioning the generated data and indicators, and there's a great discussion also in different papers in the literature. Is it really possible to detect polyethylene in the right manner, or PVC? So at the second part of my lecture, we come to some examples for microplastics in food. This is the topic here today. Here we investigated a rock salt from a supermarket, 500 grams, and we could identify around 600 microplastics and pigment particles with a size bigger than 5 micrometer. The cardbox packaging was coated with SBS, so it was not surprising that we found SBS in this package. What we also find is a lot of pigments, pigment blue and pigment yellow. and pigment violet, and all these pigments are used for the label of the card box. So that means most of these particles comes from the production process or from the ambient air. Second example is salt in microplastics in salt by Pyrolsis-GC. Here is a sample of 200 grams. At the beginning, we did a density separation because in salt is very often a lot of very small stones, and you have to remove the stones for the analysis. And here we found in this sample 38 micrograms of polypropylene, 4 micrograms polyethylene, and 12 micrograms PVC, and so on, is shown on the left side. And then we had 5 replicates on the right side. And you see is nearly the same because you have deviations. The reason is in homogeneous particle distributions. And what the most particles come from polypropylene and PVC. Third example, icing sugar, also from the supermarket, 500 grams, and here we found around 440 microplastics and pigment particles. Here was the same. The printed cardboard packaging was coated with SBS. So we found here also SBS, but here not so much the pigments. Maybe it's another factory, and the ambient air was better cleaned. The reason for the high content of the natural rubber is until yet not clear in this packaging. Maybe it comes from seals which are used in the filling station or so. Then we investigated a lot of mineral water in glass and PET and Tetra Paks and so on. Here is a comparison between a PET bottle and a glass bottle, because the bottles had a different filling. We extrapolated it to 1 liter. So you can see in the PET bottle we have 550 microplastic particles. However, it's so that double of the particles are pigment particles, because the pigments here are used also for the labels and for the printing of the bottles. So that means, for example, that we have in the PET bottle, for example, 50 pigment particles and 24 microplastic particles. And in the mineral water, we had much more particles. However, the same is here also that, for example, we have in a glass bottle, the relation 85 pigment particles to 50 microplastic polymer particles. Then we compared from another process line a PET bottle with Tetra Pak. And you can see that the content is nearly the same, around 200 particles. However, here is also the same that in the PET bottle, 70% of the particles, again, pigments, and not so much polymers. In comparison to the Tetra Pak, here is no or very low content of microplastics and very low content of pigments, and only we found polyethylene. But the outer and the inner shell of this Tetra Pak and also the cap is from polyethylene. So here's the source relatively clear. Then we investigated a process line from the spring water about the processing to the filling station and to the end product, also with different with several bottles. We compared here also reusable PET bottles. You can see 3 bottles with different content. Sometimes the bottle is clear, and sometimes you have mostly pigments in the bottle. In comparison to the Tetra Pak, here we have no pigments or very low, and instead of that, the polyethylene particles. However, the spring water is clean, so there's no entrance from the spring water. The processing water is also clean. What we found is only, I can show it here, PTFE. That means this is a part of the seals, and we used for the sampling a site, and maybe it was a long time not open, so that means here's also no entrance. So that means that the polyethylene is clear, comes from the inner cover of the Tetra Pak, and the PET bottles is clear from the bottles. And what we found, we sampled also the ambient air in this factory, and what we found is a lot of PET particles, and we found this PET particles then in the PET bottles also, because the particle size distribution for this PET in the ambient air was between 10 and 20 microns, and that same was also in the bottles. And then again, the pigments. It seems to be a greater problem that the pigments from the labels are in the bottles. What we also found here is that around, it depends, it's between 70 and 80% of the particles were below 20 microns. So we have only a very small amount above 20 microns. Most particles are below. Next example for microplastics in food, we investigated mussels here by Pyrolsis-GC, and we found PP, PET, polyethylene, and polystyrene between 1 and 5 micrograms per gram in this. We couldn't compare it with spectroscopic methods. We have no particle-related data. If you compare the end spectroscopic versus mass-based methods, we have different targets. FTIR and Raman counts particles. Pyrolsis-GC as only masses. That means in the spectroscopic methods, small particles lead to high counts, to high numbers. In comparison to pyrolysis, bigger particles leads to a high mass contribution, and we have no idea about the particle size distribution. So that's why it's not so easy to compare data. And the next is, I told you about these clusters, that in the spectroscopic methods we could clearly identify every polymer, but in the pyrolysis only the clusters, and we have to harmonize these clusters for a better comparison. This is an idea how we can do that. On the right side are the clusters for pyrolysis. On the left side, all the polymers from Raman and FTIR, and in the middle, that we build clusters that we can compare this data. So how we can do that? We tried this comparison for identical real samples. We had a comparable pollution which reflected numbers and masses. The polymer types, that means the identification is very similar. That is good. However, the quantifications can be problematic because particle into mass transformation is possible also with strict limitations. You have an ideal shape assumption for the mass conversion. That this is not really true. And so we have a trend to overestimate bigger particles. This is in progress, how we can improve it. And then in Pyrolysis-GCMS, we have very selective generated signals. The signal quality is sometimes by low detections also not so good, and the interpretation of the signals is also not for all polymers clear. At the very end, a very new method for spectroscopic analysis is the use of quantum cascade lasers in combination with so-called optical photothermal infrared spectroscopy. This device is Mirage. We had here some test measurements with very good results. You can measure with this device simultaneously infrared and Raman or infrared and fluorescence. This has the big advantage that if you use at first a fluorescence measurement, then it's only necessary to use with Raman or with FTIR the particles which have a fluorescence signal. And the greatest advantage of this device, this optical photothermal infrared spectroscopy, can overcome this limitation of infrared spectroscopy. You can go here up to particles to 500 nanometers with infrared spectroscopy. So to summarize the lecture, depending on the goal and the research question, you can use mass-based or particle-based methods. Particle-based methods produce more detailed results to numbers, particle size, and so on. Advantage of Raman is the lower detection limit, up to 500 nanometers. The disadvantage is the time-consuming measurement. What is the advantage of FTIR? You have a faster measurement, but the disadvantage is the lower detection limit of 10 microns. So the best way would be a combination of optical particle measurement with FTIR and with Raman, and then you have a complete analysis. Mass-based methods like pyrolysis can deliver results faster. However, for the quantification, you need always a good calibration. A good message is that the microplastic in food samples, I have shown some examples. The sources are usually not so much from the environment, however, mostly from the production lines. So, okay, that I could say the determination of particle size and so is possible with these methods. You have to consider some points like which microscope you use, laser wavelengths, and so on. A very important point is the subsampling. You can reduce the time of analysis, but do not reduce too much. Then the error is too high. And a new approach is the use of random forest machine learning methods instead of the use of spectral libraries. Then you can also reduce the time for the evaluation. And a very big point is also you have to transfer all results in databases for later on modeling or using, and also to have interlaboratory tests in common projects between different partners. At the very end, most of these results were done in the project Microplastic at Food with different research partners from Austria and Germany, and around 60 industrial partners. The goal was the development of a method to evaluate the presence of microplastics in food. And this is shortly shown here. We did this in this project also for packaging. Also, we investigated packaging in filling plants, water and filtered beverages, food surfaces, and soluble foods, also not so complicated matrices. And at the end of the project, we developed a catalog of measures to reduce microplastics in food. And this catalog is available in German and in English and can be found on this website. And we started half a year ago the follow-up project, Microplex Food. And here we want to try to develop standard operation procedures for more complex food matrices for the identification of the potential sources of entry. And here for that we have some more partners and also a lot of partners from the food industry. The goals very shortly, we will want to develop the standard operation procedures with different enzymatic digestion methods, and then force the development of the spectroscopic methods. And we want also to use Pyrolsis-GC for that. And at the end, investigate also the influence of packaging and process environment, and to find the sources for microplastic contamination. I have to thank my group here in Dresden and all our partners, which we work together in Warnemünde, Bayreuth, Munich, Vienna, Oldenburg, and Leipzig. And I have to thank the founding of our projects come from different sources, from European projects, from the industry, from German ministry, and GPI Oceans projects, and so on. And I thank you for your attention.
Thank you, Dr. Fischer. We are open to questions for a couple of minutes from here on. We invite anybody with questions, please unmute yourself and go ahead.
Yes, I can start. This is
Yes, of course.
Lars Bertilsson from Tetra Pak. I hope you can hear me.
Yeah.
Yeah, I'm interested in the laboratory practice of analysis microplastic, and you mentioned in the talk now that to reach sizes below 2 micron, you need clean room conditions. But what is your judgment? How far down in size can you come? For instance, working in a laminar flow bench and working without anything. What is the rough judgment from your side?
To work in the flow bags is mandatory. Otherwise, microplastics in the air is everywhere. We have also a project, microplastics in the atmosphere, and measure in the range below 10 microns, and there is enough. So you have at minimum to work in a flow bench. We have a special room with we removed all devices which come from polymers or plastics. We use only glass and steel and so on. And have also particle purgers in the room and things like that, and special clothes and so on. And then you can identify with a lower limit of 2.5, 2 microns. If you go to lower concentrations, you need really a clean room. Otherwise, you have too much particles, not microplastic particles, but a lot of other particles which are in the air. You can imagine if you stand in a room near a smoker, you have 1 million particles per cubic meter, particles in air.
Yeah, okay, we are not smoking in our laboratory, but okay.
Yes. For example, but
yes.
on the North Pole, there's also investigation on the North Pole. It's the cleanest air on Earth. You have 10,000 particles in 1 cubic meter.
Yeah. To have such a dedicated room is, of course, not straightforward. But if you are able to put a clean bench in the normal laboratory and maybe put your infrared spectrometer inside that clean bench and the filter equipment as well, is this sufficient?
For the measurement, yes. The main problem is not the measurement. The main problem is the pretreatment. You have to filter the sample. You get a sample. You have to filter the sample. You have to do an enzymatic procedure. And this procedure, this is the source for contamination. The measurement is not so the problem. The measurement can be in a special room where not the door should be closed and so on, and you have an air purger, and that's okay. if the particles are on the filter, but to bring the particles to the filter, this is the main contamination source.
Okay, very good. Thank you.
Thank you. Anybody else who would like to ask a question?
Maybe I can raise a question.
Yes, of
First of
course.
all, Dirk Martin from Südzucker, Germany. Thank you very much, Mr. Fischer, for this very interesting speech. We are already involved in the as an industry partner in the microplastic at food, and even in the following project, Microplex Food. And we also just recently established or tried to establish own laboratory for microplastic in our facilities. And we, for instance, we purchased also a clean bench and an FTIR instrument from Bruker, the Lumos 2 with an FPA. And we collected already our first experiences, and we get more or less reproducible results, but we are not sure if they are also accurate. So my question is it possible to participate also in your collaborative studies to see if...
Yes, if you a member of the user committee of Microplex Food.
Yeah, we are.
Yeah, we do in Dresden here the Raman analysis, and you should go to the University Bayreuth. He do the FTIR. He have also the Lumos, so it would be good comparable, and then you should go in contact with Martin Löder.
Okay.
Yeah.
Okay, thank you. Then we will do that.
Yeah.
Thank you very much.
Thank you. Yes, Dr. Schumann, please go ahead.
Yeah, thanks. Thanks a lot for the presentation. Very, very useful and insights. And my name is Michele Schumann. I'm Food Safety Research Manager in Barilla Company, and we are starting just now, right now, to make more experience in this field because we have just installed a photothermal instrument. So we are going in that kind of techniques that you showed between the different ones. And considering your experience showed us about the filtering solutions, have you any particular suggestion on the best kind of material and, yes, say, filter solution going to apply this photothermal IR instrumental analysis?
Yeah, so I can recommend silicon filters.
Okay.
They are commercial available. What is also possible is gold-coated polycarbonate filters. Both is possible. Both have the same price, not so cheap. One filter is around 15 euros or so. But you shouldn't use Anodisc because the surface is too rough. And particles below 5 microns, you can't find it on Anodisc.
Okay, because that was the point. We were interested, obviously, to go lower as much as possible, as you mentioned, theoretically until the 500 nanometers or 1 micron, let's say it. But you suggested do not go for the Anodisc.
No, it's not possible. We tried it, and Anodisc is cheap, very good. But if the particles are below 10 microns, it's not suitable.
Okay. So silicon or polycarbonate covered with gold?
Yes.
Okay, thanks a lot.
Thank you. We're available for a few more minutes if somebody wants to raise a question. I don't see any further questions. Then I would like to thank everybody present at the meeting here. We look forward to seeing you again next time in April for an informative and interactive webinar that is subjected to the critical overview of exposure of microplastics to human brain. We hope to see you as well on the Community of Practice on our LinkedIn website, and wishing all of you a good day. Thank you very much.
Thank you.
Bye-bye.
Thank you.
Bye. Thank you.
Thank you.
Thank you.